Welcome everyone to the second installment of Prerequisites for Calc BC. If you want to look at the last one, it was algebra. That one's up, but the other ones to come are geometry and trig. But here we have functions and graphs, so let's get started. So the first thing we have to understand about functions is what a function is. So right here I kind of have the formal definition, which you don't really need to know verbatim, but it kind of just gives you an intuition behind what qualifies as a function and what doesn't. So a function is a mapping between two sets. We call the sets the domain and the range, where one element of the first set, which is the domain, is assigned to one element in the second set, which is the range. So if I were to draw, this is the domain, this is just really abstract, but there's the domain and this is the range. A function maps from this to this. So I can take this point here and go to some point over here, and the only time that this stops becoming a function is when I have one domain value going to two different range values. So I can have two domain values going to one range value, like right here. But the moment I have, if I draw another blob, the moment I have this situation is where it's not a function. So say this is a number A. If I were to graph this, say A is right here, there's A, and it goes to two different domain values, or two different range values. There's one range value, and here's the other range value. Notice how now it doesn't pass the vertical line test. So if I were to draw a straight line up, it crosses 2 points, which disqualifies it as a function, versus here, I have two domain values going to one range value. What that would look like is just, say, here's A and here's B. There's random numbers, but if they go to the same range value, this is still a function. So if I have some weird looking thing that goes through those 2 points, this still passes the vertical line test, but this one doesn't. So this is still a function. The only time you're disqualified as a function is when you have one domain value going to two different range values. So now that we know what functions are, we can start graphing them and seeing what some of them look like. So in calculus, you're going to have some parent graphs of common functions memorized. So here we have y equals x. Hopefully you have that down, just a diagonal line. Every x input is the same y output, so 5 is 5, a is a, etc. With lines, you're going to have to be also familiar with how to write equations of lines, so slope-intercept form, and then the new one that's going to be your friend this year is point-slope form. I don't know when this exactly comes up, but you'll use that a lot. And then also, maybe even more important, is the slope formula. This is kind of what the beginning part of calculus is based on, because the slope formula gives you the intuition behind derivatives. But moving on to x squared, this is just the normal parabola shape. And then x cubed kind of looks like that. And if you ever forget what one looks like, or have a function in front of you and you don't know what to do with it, if you have the equation, you can literally just plug in values. That's what functions are meant to be. So like this, I have no idea what it looks like, but I can just go x, set up a table x and f of x, and if I plug in 1, I get 14, and just keep going until you can get like a kind of rough picture of what the graph looks like and connect the lines. But you'll never be stuck if you have a function in front of you when you're trying to graph, because you can just pick values and go from there. This line right here is kind of just a placeholder. I kind of wanted to get the intuition behind, if you plug in any number bigger than 1 for this power, you can kind of have a rough idea of what any of them look like. So looking at end behavior, I think you learned this in pre-calc, but odd powers, their end behavior is up and to the right, down and to the left, up and to the right, down and to the left. So if I picked 1, 3, 5, 7, 9, 11, etc., all of them would end up looking something like this. And then for even powers like 2, 4, 6, 8, they would all look something like this parabola. So there's that intuition. And then these fractional exponents, again, you can just rewrite these as square roots, cube root. So what this one looks like, since you can't plug in any negative numbers, the domain is anything greater than or equal to x, and it looks like that. It looks like if you took an arm of this parabola and like turned it 90 degrees. And then this one is similar, except now you can actually graph this part because you can plug in negative numbers and take the cube root without it being undefined or imaginary, I should say. And then that's like the same thing with this. You can kind of predict what any of these will look like eventually. So if I had x to the 1/2, 1/4, 1/6, etc., I can't take the roots of those if the input is negative. So they're all going to have this domain here, but they're just going to get lower and lower and closer to the x-axis. And the same thing here, they're just going to get closer to the x-axis. And then these two are reciprocal functions, so this right here is 1 over x. This one looks kind of funky, but I think it looks cool. There's that. Sorry, this is weird at the bottom of the page. Kind of looks like that. So it goes off and to the right, off and to the left. But if you approach 0 from the right, it actually goes up to infinity. And if you approach 0 from the left, it goes down to negative infinity. So that's what that looks like. And then this one over here kind of looks like if you took x squared and like cut it in half and flipped them, if that makes any sense. So this goes, if you approach 0 from the left or the right, both approaches infinity. So here we have e to the x and ln of x. I was trying to make a table here, but it's very difficult with this bottom of the page situation. But anyway, if we pick good values for this, we can figure out what the graph looks like. So plug in 0. I'm going to give up. Plug in 0, you get 1 because e to the 0 is 1. Plug in 1, you get e, and plug in -1, you get 1 over e. And e is about like 2.7, but anyway, so here's 1, and here's like 2.7-ish. So there's a point here, and a point here, and it just looks like any old exponential. Kind of like coronavirus. Just kidding, too soon. And then ln of x looks exactly like that, except flip-flopped, and now it's, instead of approaching this axis, it kind of approaches this axis. This is so hard to write. I'm not going to do this. There we go. So as you go closer and closer to 0 from the right, it goes down further and further to negative infinity. And if you ever are stuck on what that looks like, I'm not even going to try to make a table. If you have x and ln of x, remember if you plug in 1, ln of 1 is 0. So that's this point right here is 1, 0. And then if you plug in e, you would get ln of e equals 1, which is like right here. Anyway, that's generalizable for any like log or exponent thing. Just pick good values and you can make the graph of any of them. And here are the last essential ones that you need to know. So here's absolute value of x. Just looks like if you took y equals x and took the third quadrant of it and put it above the x-axis, because it's always going to be positive. And then sine x, cosine x, and tangent of x. These are kind of annoying, but if you remember, sine of 0 is 0. So that's the graph that goes through the origin. And then plug in pi halves, if I can write with this pen. Pi halves, and you get the maximum of 1. Pi halves, 1. And then if you have pi, it goes back down to 0. And then you just keep doing that. Same thing with the left side. And then cosine of x looks exactly the same as that, except it's shifted over pi halves. So it goes through 1, 0, or 0, 1, because cosine of 0 is 1. And then if you plug in pi halves, it's 0. And then if you plug in pi, it's -1. So, boom, something like that. And there's those two. And our last trig function is tangent of x. I know there's other ones out there, like the reciprocal ones, like cosecant, secant, cotangent, and all the inverse ones, but you don't really have to have pictures of graphs of those memorized. It's just the three basic ones, sine, cosine, and tangent. But if we rewrite tangent as sine over cosine, now it's easier when we pick values. So if we make a table of x and f of x, if we pick 0, sine of 0 is 0, cosine of 0 is 1, and 0 over 1 is 0, so we have a point at 0, 0. And then if we pick pi fourths, sine of pi fourths is root 2 over 2, cosine of pi fourths is root 2 over 2, and root 2 over 2 over root 2 over 2 is 1. So pi fourths, 1. And then if we plug in negative pi fourths, we get negative 1, because sine of negative pi fourths is negative 1. So if we plot those, here's pi fourths, here's negative pi fourths. So we have 0, 0, pi fourths 1, negative pi fourths, negative 1, 1, negative 1, 0. The graph of tangent just looks like, kind of looks like cube root of x, except it's periodic, so this pattern repeats every pi. So as we approach pi halves, this graph goes up to infinity. It never quite touches pi halves because cosine of pi halves is 0, and dividing by 0 makes it undefined. And the same thing at negative pi halves. This is an asymptote, a vertical asymptote, so it never quite hits negative pi halves, but it approaches negative infinity as you approach negative pi halves from the right. So this is one period, and this just repeats the same way cosine and sine do. So there's the last trig one. I also realized I forgot, even more basic than y equals x is f of x equals c, which is just like f of x. Let's graph f of x equals 3. Here's 3, and now my function literally is just a horizontal line. So anything I plug in for x doesn't matter. All I'm going to get out is 3, and that's what yields that horizontal line there. And transformations are just taking the graphs we just learned and moving them around. So I'm assuming you're pretty familiar with this already, so I'll just breeze through. So if we have y equals x squared, we know that looks like that. So there's the parent graph. If we want to move that up and down, we just add any number to it, x plus c. And so that's horizontal shift. Vertical shift, probably easier to think about, but there you go. We have a new function where this right here is c. And then if we want to move it horizontally, this one's a little harder to think about, so I'll do as best I can. You take this input, here's the input x, and you put in, if you want to shift it left, you would go x plus 1, and this whole input value x plus 1 replaces that x. Or if you want to shift it right, you would have x minus 1. This whole input value replaces this x. So it's kind of hard to think that x plus 1 squared would be left of x squared, because plus means adding, and you'd think that adding would mean moving it to the right. But how I think about that is, so I plug in 0 here, I get 0. I plug in 1, I get 1. I plug in 2, I get 4. If I plug in 0 here, I get 1 squared. So right off the bat, it's already different. If I plug in 1, I get 2 squared, which is 4. 2, 3, 4. And if I plug in 0, if I plug in negative 1, I get 0. So you can kind of see how this shifts left because you're adding 1 to every x value. And that's how it goes over here. And then if you want to shift it right, you subtract. So if I plugged in 0, I would get negative 1 squared is 1. If I plugged in 1, I would get 0. If I plugged in 2, I would get 1. And yeah, that's what that one would look like. And so that's horizontal shift. Vertical shift, probably easier to think about, but there you go. And now if I graph it, it turns into below the x-axis instead of above the x-axis. And the function is negative square root x. So right here, if I plugged in 4, I would get 2, and if I plugged in 4 here, I would get negative 2. So all the output values are multiplied by a negative number, which is why they're reflected over the x-axis, because all the output values are multiplied by a negative 1. And then over here, if we want to reflect over the y-axis, so we'll use square root x again. Instead of multiplying by a negative outside, so negative f of x, that's for that. We multiply, or we take the function and we go f of negative x. And what that means is we take this input value, negative x, so here's our function, root x, and we take negative x and put it in for x. So now our function becomes square root of negative x. So wherever you see an x, I started with x, instead of an x you would put a negative x. So now it becomes negative root x, or root negative x, sorry. And what this does, it reflects over the y-axis, so now it's facing this way instead. The reason behind that, so if you remember the domain here could only be positive, because if we plugged in a negative number, it would give an imaginary number, but here we have to plug in negative numbers, because if we plugged in a positive number for x, it would give us an imaginary number, which is why now it's facing that way instead of that way. So that was part one of functions and graphs. It was getting kind of long, so I decided to split it into two. But the next part is going to have compositions and types of functions or categories of functions, which is also stuff you have to have for Calc BC. But thanks for watching this one. I'll see you in the next one.